Take a look. The first section was, I was after a few terms. So quantized was what I was after, is the word that describes a value that can exist in one of two possible discrete states. That was the chemist on stairs or the chemist on a ramp. Chemist on the stairs talks about quantized values. Ground state is the lowest allowed energy state for electrons can have. Because they buzz around an atom. Now, an atom, the subatomic particle that's most important for giving an atom energy is its electrons. Electron orbital is a region of space where you find an electron. Nucleus is the center of an atom. Excited state is kind of the opposite of ground state, is where the electrons are at an energy state above the lowest energy state. Valence electrons are the outermost electrons of an atom. Mass number, or the symbol A, is the sum of protons plus neutrons. Atomic mass units is the units that we use for saying how much an atom weighs. And I was after grams per mole as the units we use for molar mass. The answer for J is isotopes. The atoms are the same element that have different masses because they have different neutrons in their nuclei. That's J, isotopes. So then I asked some questions about electrons and subshells and orbitals. So some of them are tricky. These were each worth 1 point. How many orbitals can you find in a p subshell? And the answer is 3. A p subshell, you guys would tell me, can accommodate 6 electrons, but there are 3 orbitals in a p-type subshell. B, how many orbitals are found at n is equal to 3? And this is like where I kind of did the onion on the board. So when n is equal to 1, there's only one type subshell. When n is equal to 2, we have 2s and 2p. When n is equal to 3, then's when we get the 3s, 3p, and 3d. And if you add up all of those orbitals, it's 9. There's like a quick and dirty way. It's actually n squared. If you want to know how many orbitals there are in a given principal energy level. And so 3 squared is 9. So that's what it looks like. Let's see. C is probably one of the trickiest ones. And it's actually the answer is 2. Okay, the maximum number of electrons that can occupy A, as in a single d orbital. I know. So most people put like 10, so you're in good company. But only 2 can be shoved into one room. Question D, I know. D, what's the lowest n where you finally kick in and get the F-type subshell, and that's n is equal to 4. E, what is the shape of an S-type? Oh, wait a minute. If it's a spherical shaped orbital, it must be an S-type orbital. That's the best answer there. And then on to the next page. Okay. So I was grading 3. That was where I gave you information about the element potassium and had you come up with the average atomic weight. It dawned on me that I should have told you I'm going to be facetious. I should have told you there'd be one of these on the test. I'm like, wait, I did tell you there's going to be one of these on the test. So that's just to say, in preparing for your unit exams, in this class anyway, if I give you a list of things that are going to be on the test, you probably should make sure you can do all those. It's like a checklist. So in order to come up with those decimal numbers, the average atomic weights for each element, we have to go out into nature and see how many different isotopic forms there are in the relative abundances and how much each one weighs. So when you go ahead and do it's like a type of weighted average where you take how much each one weighs times its fractional abundance plus how much it weighs times its fractional abundance times how much it weighs times its fractional abundance. You add those together, and it should match the number on the periodic table. So this was worth 5 points. So this is an example where if you got the right number but didn't put the right units, okay, I took off a point. And I did go ahead and at the top say round to 2 decimals. So those are the sort of things that you'll get partial credit for. The next 2 sections, we take for granted that, or I do teaching this class, that everybody kind of knows their way around elements. Hey, Austin. and knows kind of to match up the symbol with the name and the name with the symbol. So I'll just kind of let you look at those. By the way, your final in December in this class is comprehensive. So that's to say that you're going to run into these similar concepts, okay? They aren't going away.
So is it like cumulative?
It is a cumulative and comprehensive, yes.
So it's like everything from all of the
Yes.
chapters?
Yep. And as we get closer to the final, I'll give you some hints. I don't know if I already told you guys for the final, what I've done usually in this class is you can bring a doctored up periodic table. So basically, you have some classes let you bring, some notes or a note. It'll be a single sheet, but you can't, how do I say this? You have to use my periodic table, like my one that has no names on it. But if you want to write the names in, that's fine. Okay, so for your final exam. So one side will be that black and white periodic table. You can write names. You can kind of put at the top of the columns information about the elements, and on the back will be totally blank for you to write on. Okay. So that sometimes students are like, "I'll start working on that now." So that's kind of how that works. So these were all questions about the subatomic particles. Protons are allowed to coexist in that small nucleus because of the presence of neutrons, so that's what I was after there. Positively charged are protons. Not found in the nucleus, electrons. Determine what an element is, protons. Have a mass of about 1 AMU, that is the protons and the neutrons. Most attracted to the positively charged protons, the negatively charged electrons. G is kind of related to E, so what gives an atom mass against the protons and the neutrons. We'll be talking more about H in Unit 3. H is the outer subatomic particle of the electrons, and they are important when the compounds are formed. So I, positively charged particle, is a proton, and J, if you put neutrons and electrons, I was fine with this, but I'm alluding to isotopes here with J. Can atoms have the same atoms of the same element have different number of neutrons? And they can differ in electrons too, but some would argue now they're not an atom, now they are an ion, so I don't know, it's a matter of semantics, but you had to at least put neutrons for that one. And then 7 was worth 5 points, and so the mass numbers in the upper left-hand corner, that, remember, is the number of protons plus neutrons, and the atomic number is in the lower left-hand corner, that is 47 for silver. That's the number of protons, so B and C were the same. Number of neutrons we get by difference. It's the mass number, the big number, minus the number of protons gives you neutrons, and I did use my calculator for that one. Number of electrons, in this case, since it's neutral, again, we'll be talking about neutral atoms and ions. And since I told you that there's no little plus or minus in the upper right-hand corner, then it must be neutral. The electrons equal the protons, which is 47. So then the last subject we covered in lecture was this idea of how big is an atom. And we said that atoms increase as you go down the same group, and atoms kind of somewhat counterintuitively decrease in size as you go from left to right. Or they increase in size as you go from right back to left again across the same period. So if you find these on the periodic table, aluminum's bigger, potassium's bigger, and tin is bigger. All right. So then number 9, you need to draw the arrow diagram. I can't remember this semester. Usually there's maybe one student who draws the arrow diagram and it's not quite exactly right, and then they use the arrow diagram and they apply it to their electron configurations. And I try to kind of catch that and give you a break down below. But then I was after box and arrow notation for silicon and magnesium. So that's where those are. These were both worth 2 points apiece. And so, it's possible that you missed a point here and there. Remember that, like for instance, with silicon, if we kind of peter out finding homes for electrons in a subshell, 3p, of course there are 3 orbitals in that subshell. We have to draw all 3 of them, even though we're only going to put 2 electrons there. Down there at the bottom, this. Okay, so this was one, yes, I thought of Becky. She didn't like these density ones, right? Okay, but this one actually, we had density there, and if you're ever faced with a problem like this, and some of you did a very good job of doing this, you basically pulled those numbers out, you pulled the density out, and you kind of wrote it aside so you could use it as in your problem, okay? So 7.87 grams per milliliter means, sorry, 7.86 grams per 1 milliliter, that's the density. We're dealing with iron, and the decimal number for iron is 55.85. That means 55.85 grams per 1 mole. And in this case, we were given moles and trying to get volume. So I always start with kind of the number that's not the molar mass. So 1.32 moles. Then I use the molar mass to go ahead, the unflipped version, so moles cancel, left with grams. And then I can insert the flipped version of the density, 1 milliliter over 7.86 grams. So grams cancel left with units of milliliters. So round to 3 significant figures. There she goes. Okay, so there's that. And I don't have it posted on, the answer key's not posted yet, but I will. One thing about it, either now or at some point, you're probably gonna want to double check that I added up correctly, all of the points. So the way I grade is in the lower right-hand corner is the number you got right on that page. And then all I do is go flip through and count circled numbers on the bottom of the page. So that number should add up, and I do use a calculator because my husband does this too, and he does it in his head. I'm like, really? So I use a calculator to see, add that up and put that number on the front. Okay. So that number's in the grade book now. So this morning, or kind of as I graded them this weekend / this morning, I came up with a list of things that if you're looking to do better in this course, and these actually could apply to maybe other courses, I came up with some suggestions. One is actually specific to this course. I use the online component for the grade book, and I also use the online component for posting solutions to homework and to your, I mentioned the answer key to your unit exams out there. The second one up there is if you're looking for, actually the next two, to me, chemistry becomes easier the more problems you do. And I know it's like, oh, are you serious? Yes, I'm serious. Okay, it's kind of like if you play an instrument, like I do. We had a concert this weekend, which was a lot of fun, but if you play an instrument, the only way you're going to get good at the instrument is playing it. So anyway, you have 2 opportunities. I said at the end of the lecture notes are work all lecture guide problems. So actually it's the beginning. Okay, these are what I mean. These are lecture guide problems. Now, I don't assign all of these because, frankly, I don't want to grade them all. Okay, but the answers to the odd ones are the back of your book. So that's a possibility. The third thing up there, you can, if you want to, just let me know, borrow like a intro Gen Chem textbook from me, and it will have other problems that you can work where the answer's in the back of the book. That's a thought. Number 4, I don't know if everybody knows this because I say it at the beginning of the semester, and some people take me up on it, but I do record pretty much success. My success rate's about maybe 98% success rate of pushing my videos out there. So every time I am in here doing this, okay, you could actually see it and hear it. Okay, I had one student the other day say, I just like listening to him because I like to hear the questions asked. I'm like, okay. They like to hear themselves on the video.
That's why I don't want to. I hate hearing myself. I'm like, what the heck?
Oh, JC.
It's weird.
So it's a thought. The other thing is every Wednesday, and especially the Wednesday before exam, for some reason, sometimes students really take me up on that. Every Wednesday, and you guys' exams are always on a Thursday. Every Wednesday at 3 in the library, there's a study group. I didn't write it up here, but feel free to get your own study group together if that's a thought. And then just to remind you that right before this class, at least I'm here by 9, and so I said from 9 to 9:30 I would entertain any sort of questions you have. Okay? Now about 9:30 to 10 I'm kind of ramping up for this class, so that wouldn't be a very good time. And then right after this class, from 11 to 1:30, Monday, Wednesday, Friday, or by appointment. So, that's all. I'll go ahead and I am trying to get a tutor for this class. So I think I'm close finding our way through that. So if you're interested in a tutor, the best thing to do is stop by the Success Center, and I think you have to fill out a paper or something, and they'll connect you up with a tutor. Hey, it's free. Any questions about all this? Every once in a while, I make a mistake on the test. So the best time to say, Mrs. Snipes, I think you missed this point that I earned is outside of class. And I go, oh, yeah, I did. Okay? All right. So let me put a plug in for Thursday's lab. Now, you guys are pretty good at coming to lab. Oh, let me go ahead and pick up your homework. And you can keep the test. I'll pick up your homework, though. Thursday's lab is, we're going to talk about naming compounds, naming ionic compounds. And so Thursday's lab, how do I say this? For your next exam, the stuff we cover in Thursday's lab is going to be like a quarter to a fifth of that test. Your Unit 3 exam is like stuff we're going to hit in lab on Thursday. Okay, so please don't. It will be a good thing, right? So before we get to Thursday's lab, though, we need to talk about, we have a couple of sections to get under our belt, so we'll see how far we get. This idea of compounds. Okay, so it's like, is she bringing up that same, you guys don't have this, is she bringing that up? She's just like, so we're focused, we talked a lot about elements, and now we're talking about compounds. And I'm going to have to use my finger because my little, I ran out of my, stylus. So, we talked about elements, okay, atoms of elements, and elements can be built up to make compounds by a chemical reaction, CHM122. We'll talk more about chemical reactions in Unit 4, I think, in here. You can take a compound and break it down into its elements by chemical reactions. So we're talking about compounds here. All right, so what is a compound? Well, the next slide actually gives you some examples of compounds. We use a chemical formula to say what atoms are connected together in that compound. Yeah, like water, exactly. So a compound, here's the criteria for a compound. It needs to have one repeating unit, and again, that repeating unit is, we use a chemical formula to say what that repeating unit is. That compounds can be broken down. Okay, I used just a minute ago, I said they can be broken down all the way into their elements, okay, by one way or the other. And down here, this third one says that with a compound, it needs to have at least 2 different types of elements that are stuck together. Now, this right here, kind of buried in here, okay, atoms chemically combined. So I think it's underappreciated. You guys would say that, of course, H2O. I think I've done this example before. So H2O has an oxygen with 2 hydrogens stuck together, or stuck to what we call the central oxygen, 2 hydrogens branching off of that. It kind of actually has this sort of boomerang shape, and we're going to talk about why water has that what we call a bent shape instead of a linear shape. Okay. But when we talk about the chemical bonds, we have 2 chemical bonds here. Actually, I guess we just have one chemical bond joining the oxygen and the hydrogen, another chemical bond joining the oxygen and the other hydrogen. Okay, so those are chemical bonds. CHM122. Those are chemical bonds. So, And there's a lot of things in, especially biology, I think, where you're not quite, it has some kind of different possibilities, but these have definite structure. So here's a list of some different compounds, some different chemical compounds. And in all of these set of atoms are stuck together with chemical bonds. Can the chemical bonds be broken? Yep. But it'll take some sort of chemical reaction will occur. And I might have done this before, but I want to pick on, for instance, ammonium sulfide right quick. So, how do I say this? Did I already do this before? Okay. So this has a central sulfur atom, okay, and then it actually has two NH4 groups. So I'm going to write an NH4 group up here, NH4, and I'm going to write an NH4 group over here. Then I need to stick my sulfur with my NH4. So I'm going to go ahead, I'm just going to do a dotted line here from that sulfur to that nitrogen, and a dotted line here from that sulfur to that nitrogen. And I know it looks kind of blobby up there. If I were to circle my NH4 groups, this is kind of what we have going on here. So that is NH4 quantity 2, because you see the 2 up there, 2S. So how many hydrogen atoms do we have in that repeating unit? 8. We all buy that? I agree. Very good. So let's ask a similar kind of follow-up question down here. So it gets, I don't say necessarily tricky, but anytime you see a quantity like this is actually NO3, we're going to talk about that. That's nitrate, and this is magnesium. So this is magnesium nitrate. But we can see we have nitrates. We have 2 nitrate groups. How many oxygen atoms do we have in one MgNO3 quantity 2? How many oxygen atoms? 6. Yeah. So I just wanted to make sure we're all on the same page there. So for H2O, I don't put H2O1, but I could. H2O, that would be the same thing as H2O1. And sometimes as we get started, sometimes students feel better putting that subscript 1 there, and I'm fine with it either way. All right. So we'll be adding to this list, I think. But one of the things, compounds are not all created equal. There's 2 broad types of compounds. And I think I mentioned this when we talked about classification of matter earlier. So the 2 broad types of compounds, a lot of times I will kind of list them out like a little tally. And like I said, we'll add to this. We have molecular. My abbreviation for compound is CPD. And then we have ionic, CPD. Okay, molecular compounds and ionic compounds. A synonym for molecular compound, I'll go ahead and put it under the column, molecular compound. I'm going to say equals covalent compound. Same thing. Sometimes you'll hear me go back and forth between those 2 terms meaning the same thing, molecular and covalent compound. So this thing in italics, I'm actually going to go ahead and put that on my little tally sheet. It says molecular compounds exist as molecules. So exist as molecules. And we contrast that to ionic compounds exist as formula units. It's funny because we tend to, if you're trying to kind of throw a word out there, not thinking the nitty-gritty of chemistry, we say a lot of things are molecules when they're really formula units, but that's okay. All right. We have something else to add to our tally here. We talked about one way to separate elements. We talked about that JAG in the periodic table. You guys told me these guys over on the left are metals. These small group, kind of a triangle, are nonmetals. So metals bonded with nonmetals produce ionic compounds. So I'm going to go to my ionic compounds, and I'm going to say metals with nonmetals. And for my molecular or covalent compounds, I'm going to say nonmetals with nonmetals. Oops. Actually, another way over here on the molecular or covalent side, nonmetals with nonmetals, sometimes I just say no metals allowed. So you look in the formula, and if it doesn't have any metals, then it must be over here. Okay. I'll go ahead and tell you for your Unit 3 exam, I know it seems like you just took your Unit 2 exam, but for your Unit 3 exam, I'll have like a list of compounds, and I'll ask you which one are they classified, and you'll look for the metal. If there's no metals, it's molecular or covalent, and if there is a metal, it's ionic. Now, one more thing about this. I'm going to say the element hydrogen, H for hydrogen. Hydrogen is considered nonmetal at this point in this class. Hydrogen is considered non-metal. So if hydrogen is there, that's a non-metal. Okay? All right, a couple of my movies that don't work. Okay, but going back to the movie won't play, but do you see where if somebody gives you a chemical formula N2H4 and they ask you, is that molecular or ionic, you need to have a periodic table handy, draw in your JAG, and find those elements on the periodic table. So nitrogen, I clearly have it a nonmetal, and I told you hydrogen's a nonmetal. So like the caption on the slide says, that's a molecular compound. Similarly, N2H4 is a molecular compound, so is NH3 for the same reason. Okay. Methane, CH4, find where's carbon? Oh, okay, it's on the right of the JAG, so it's nonmetal. Yeah, oxygen's nonmetal. So the cool thing, and I'm going to kind of contrast this with, this is a water molecule. The cool thing with water, which is a molecular compound, and the repeating unit up in this figure here is an H2O molecule, not a formula unit. It's like that specific oxygen, we know for sure, has a chemical bond with those two hydrogen atoms. It's like a family. It's like a unit. And let's contrast this to ionic compounds. So if somebody gives you the formula NaCl, okay, you're like, now is it ionic or is it molecular? Well, if you find a metal, then it has to be ionic. So if you find chlorine on the periodic table, wait, that's a nonmetal. Well, if you find sodium on the periodic table, that's a metal, and it is definitely an ionic compound. Potassium bromide, potassium, definitely a metal, so that makes an ionic compound. So the thing about ionic compounds is, and I'll put this up here, what's on this slide, I'm going to add it over here to ionic compounds. Ionic compounds, in their solid state, they form crystalline lattice structures. Crystalline lattice structures. They form crystalline lattice structures in their solid state. So this kind of alternating green, purple, okay, that actually is showing you a crystalline lattice structure of sodium chloride. So unlike the water molecule where you could sink your teeth into that one oxygen had kind of possession of those two hydrogens, the fact that this kind of crystalline lattice structure up here, actually each, and it's on my next slide, maybe it's on my next slide, each of the chlorines in this case actually bump up against 6 sodiums. So you really can't you can't isolate it. So they call a repeating unit a formula unit, and they don't have the family thing going. They have more of a commune thing going. That's what I think of it. So if we pick on sodium chloride, if you kind of look at the figure before, like I said, each chlorine is surrounded by 6 sodiums in its solid state, and each sodium is surrounded by 6 chlorines. So you're like, which goes with which? I don't know. You just pick a repeating unit. All right. So I'll put these both up here. So you kind of see covalent and ionic, but now it's not compounds, it's bonds. Covalent bond and ionic bond. So a little bit ago, when I drew a water molecule, I'll go ahead and draw it up here again. I had my oxygen chemically bonded to that hydrogen, chemically bonded to that hydrogen. So when I drew that chemical bond, we'll talk more about this, not this Thursday, but next Thursday. When I draw that dash there, that's a chemical bond. That actually is a pair of electrons. I'll put 2 electrons shared. And 2 electrons shared over there. 2 electrons shared with the first hydrogen, and a different 2 electrons shared with the second hydrogen. That's what connects those 3 atoms together. Electrons are shared. Okay. And so we call these types of chemical bonds, those bonds are covalent bonds. That's it. Now, let's pick on sodium chloride and talk about an ionic bond down here. My video didn't work, but I'll show you what you would have seen with the video. How's that? Okay. So sodium chloride, the formula is NaCl, right? All right. So here's what happens. Na, by the way, is a metal. I'm going to go ahead and just put an M for kind of the generic metal. And the non-metal, I'm just going to put an kind of, sometimes we'll call that an X, kind of for the non-metal. But what sodium does, we'll talk more about this, is it basically gives up 1 electron. I'll do it this way. I'll write an Na down here, and then over the arrow, I'm going to say gives up 1 electron over the arrow, and then here we go. Sodium sodium always has 11 protons. So if it's neutral, it has 11 electrons. Now it gave up 1 electron, so now it has 10 electrons. By that. And so now it's running around deficient 1 electron, so it has actually now a +1 charge. Okay, so that's cool. And then let's look at chlorine. I'll put chlorine in green here. Chlorine actually then will pick up 1 electron, which sodium conveniently gave up. Picks up 1 electron, and it becomes then, let's see, neutral chlorine, 17 protons, 17 electrons. Chlorine with an extra electron is now got, what, 18 electrons and 17 protons. So now it is got a surplus of electrons, and it's specifically 1 extra electron, so it's a -1. I kind of think of it as stepwise. And then the last thing to occur is this thing. So now we are positioned with an Na plus and a Cl minus after an electron was transferred. See how complicated it is? And then for me, I do a dashed line showing that showing a chemical bond But in this case, this is a chemical bond between something that's positive and something that's negatively charged. We call that an ionic bond. So that's our ionic bond. Okay. So it's kind of a three-deal sort of thing. So the metal gives up an electron, the nonmetal takes in an electron, then we have a positively charged something and a negatively charged something, and then they come together to form a chemical bond. So down here, under my last thing, I'm going to say electron was transferred. E was transferred instead of shared. I cannot spell this morning. All right. Cool. So one last thing before we go. Let's go ahead and add one more thing to our little tally up here. So an ionic compound, I almost think of this type of contamination. If you have a compound that has just even one ionic bond, it doesn't have to have all of the chemical bonds have to be ionic, just one. Okay? So I'll say at least one ionic bond. Whoa, I hit jackpot there. And over here for covalent compounds, molecular compounds, this is all, electrons are always shared. Electrons are always shared. So this is all sharing of electrons. In other words, all sharing of electrons, in other words, all covalent bonds. Cool. Well, I think that's a good place to leave it. And I will take a picture of this and push it out on Twitter for my grandchildren to see. I don't have any grandchildren. But anyway. So we'll see you on Wednesday.